Alrighty then, moving on to the next section, which is Advanced Types, Chapter 19, Section 3. Let's get it. Advanced Types. The Rust type system has some features that we've mentioned in this book but haven't yet discussed. We'll start by discussing new types in general as we examine why new types are useful as types. Then we'll move on to type aliases, a feature similar to new types but with slightly different semantics. We'll also discuss the apostrophe type and dynamic size types. Okay, we're going to discuss a lot of things. They mentioned a few things. What did they mention? They mentioned new types. They mentioned aliases. They mentioned this thing, which I'm not exactly sure what that means, and dynamically sized types, which we did hit on at one point in time in the past, I believe. Note, the next section assumes you've read the earlier section using the new type pattern to implement external traits on external types. And that was chapter... Yeah, I think that was the last chapter. Just to verify. Yes, we did. This is the wrapper. We read that. Yeah, I just assumed. Okay. Using the new type pattern for type safety and abstraction. The new type pattern is useful for tasks beyond those we've discussed so far, including statically enforcing that values are never confused and indicating the unit of a value. You saw an example of using new types to indicate unit in listing 19-15. Recall that the millimeters and meters structs wrapped U32 values in a new type. If we wrote a function with a parameter of type millimeters, we couldn't compile a program that accidentally tried to call that function with a value of type meters or a plain U32. What they're stating here, they made us recall this 1915, which I vaguely recall. That was like a week ago for me. But we did do something. We had millimeters and meters, and I believe we overloaded the add struct, so we can just add two different units of add two structs that are values of two different units. So we did it. We overloaded the add to account for the variance in the metric. Another use of the new type pattern is in abstracting away some implementation details of a type. The new type can expose a public API that is different from the API of the private inner type if we use the new type directly to restrict the availability functionality, for example. Okay, this is talking about wrapping something. To be clear, let's go back to this example so it's fresh in my mind and your mind. Mostly my mind. In Chapter 10, in the Implementing a Trait on a Type section, we mentioned the orphan rule that states we're allowed to implement a trait on a type as long as either the trait or the type are local to our crate. It's possible to get around this restriction using the new type pattern, which involves creating a new type in a tuple struct. I see. A new type pattern is just creating a struct that wraps a tuple of something that we want to use. And I guess it's just a wrapper per se. Here they're using new type to get around the restriction of the implementing a trait on a type that we don't own, and we don't own either of them. Okay, so let's go back to this. Another use of the new type pattern is in abstracting away some implementation details of a type. The new type can expose a public API that is different from the API of the private inner type if we use the new type directly to restrict the available functionality, for example. Now that I have a better understanding of new type, which is just a wrapper, when you wrap something, you completely control the new API, and you could map it to the inner API, or you could ignore it completely. Understood. New types can also hide internal implementation. Yes. For example, we could provide a people type to wrap a HashMap I32 string that stores a person's ID associated with their name. Code using people would only interact with the public API we provide, such as a method to add a string to the people collection. That code wouldn't need to know that we assign an i32 ID to names internally. The newtype pattern is a lightweight way to achieve encapsulation to hide implementation details, which we discuss in the encapsulation that hides implementation details section of chapter 17. Wow, it's an explicit chapter. Well, chapter name, I mean. But yeah, now that I have my head wrapped around this, we're just wrapping some code, and just to make a public API that is something that we'd like, and so that the user doesn't have to worry about how the internals work at all. Encapsulation in a nutshell. Moving onward. Creating types synonymous with type aliases. Along with the newtype pattern, Rust provides the ability to declare a type alias to give an existing type another name. For this, we use the type keyword. For example, we can create the alias kilometers to i32 like so. Alright, so this I have seen in Rust code randomly around the internet. But yeah, you create your new type based on an old type. So they can't pass in i32, but they can pass in kilometers. Now, the alias kilometers is a synonym for i32. Unlike the millimeters and meters type we created in listing 19-15, kilometers is not a separate new type. Values that have the type kilometers will be treated the same as values of type i32. And what they're really trying to say here is that they have the same API. They're synonymous in terms of everything they can do. So here we have type kilometer, i32. We have let x equal blah 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 blah. Let y equal kilometer equals 5. So you declare its type, and then you can add them together. And let's test that out just to make sure it works. Coming to the editor. Terminal. Cargo format. Prettify. Cargo run. And added completely correctly. So 10. Cool. 5 plus 5 equals 10. Because kilometers and i32 are the same type, we can add values of both types, and we can pass kilometer values to functions that take i32 parameters. However, using this method, we don't get the type checking benefits that we would get from the new type pattern discussed earlier. Okay, so I might have been slightly wrong. It seems as though they might be synonymous completely, as in anything that wants an i32 as a parameter, you can pass in kilometers. So this might just be syntactic sugar just to make your code look cleaner. The main use case for type synonyms is to reduce repetition. For example, we might have a lengthy type like this. Okay, box, dynamic, function, plus send, static. Cool. Writing this lengthy type in a function signature and as type annotations all over the code can be tiresome and error prone. Imagine having a project full of code like that in listing 19-24. So this is the thing that we're complaining about, and then writing it each and every time, that just seems annoying. But you could alias it. So I see this is the main use case for it. So it's still cleaning up your code. I was just wrong about I thought initially that you couldn't use kilometers and i32 synonymously. I was wrong. My apologies. Turns out you can do that. Alright, going back here. A type alias makes this code more manageable by reducing the repetition. In listing 19-25, we've introduced an alias named thunk for the verbose type and can replace all uses of the type with the shorter alias thunk. And then that just makes our code look a lot cleaner. And you have one reference. This code is much easier to read and write. Choosing a meaningful name for a type alias can help communicate your intent as well. Thunk is a word for code to be evaluated at a later time. So it's an appropriate name for a closure that gets stored. Type aliases are also commonly used with the result TE type for reducing repetition. Consider the standard IO module in the standard library. IO operations often return result TE to handle situations where operations fail to work. This library has a standard IO error struct that represents all possible IO errors. Many of the functions in standard IO will be returning result TE, where E is the standard IO error, such as these functions in the write trait. Okay, so we have the standard error, standard format. Here's the write trait, right? And it has write, flush, write all, write format. Cool. And we see at the end of these, they're always returning the result and error. Nothing if it's okay, and an error if something fails. The result ... error is repeated a lot. As such, standard IO has a type of alias declaration. Oh, it does. I've seen this in code. I didn't know it was an alias. Understood. Type result T equals standard result T and then standard error. Because this declaration is in the standard IO module, we can use the fully qualified alias standard IO result T, that is a result TE with an E filled in as the standard error. The write trait function signature ends up looking like this. Result usize. Yeah, I have seen this. I didn't know they were doing that though. That's good to know. The type alias helps in two ways. It makes code easier to write, and it gives us a consistent interface across all of the standard IO. Because it's an alias, it's just another result TE, which means we can use any method that works on result TE with it, as well as special syntax like the question mark operator. Understood. This is an easy way to refactor. Moving on. The never type that never returns. Ooh. Rust has special type name apostrophe that's known in type theory lingo as the empty type because it has no values. We prefer to call it the never type because it stands in place of the return type when a function will never return. Here's an example. Function bar apostrophe means that this function will never return. It will never reach the end. What scenarios do you want your function never to reach the end? Even in servers, they eventually stop. I mean, they can stop. I mean, would you put this for a server? Nah. I don't know. Let's move on. This code is read as the function bar never returns. Functions that return never are called diverging functions. We can't create values of the type apostrophe, so bar can never possibly return. But what use is a type that you can never create values for? Recall the code in listing 2-5. We reproduced part of it here in listing 19-26. 2-5. That was years ago. But okay. Oh, I think it was the guessing game. Let guess, U32, match, guess trim, parse. You're parsing out the answers. And if it has a number, return OK. If it doesn't, continue. Ignore the error. Or continue on to the next iteration of the loop. I remember that. That was a while ago. At that time, we skipped over some details in this code. In Chapter 6, the match control flow operator section, we discussed that match arms must all return the same type. So, for example, the following code doesn't work. Ew, this is returning hello. Does that mean continues returning a number? A U32? What? That's kind of crazy. The type of guess in this code would have to be an integer and a string, and Rust requires that guess have only one type. So what does continue return? How were we allowed to return U32 from an arm and have another arm that ends with continue in listing 19-26? As you might have guessed, continue returns an apostrophe value. Wow, it never returns. That is, when Rust computes the type of guess, it looks at both match arms, the former with a value of U32 and the latter with a apostrophe value. Because apostrophe can never have a value, Rust decides that the value of guess is U32. The formal way of describing this behavior is the expression of the apostrophe can be coerced into any other type. We are allowed to end this match arm with continue because continue doesn't return a value. Instead, it moves control back to the top of the loop. So in the error case, we never assign a value to guess. Okay. So quick summary. The continue here, it's returning an apostrophe, which is a never return. And they specify that the apostrophe can be coerced into any type in terms of just the Rust syntax, not literally, because it's not going to return a 0 or a 1 or something like that. It's just not going to return, meaning that guess never gets assigned when we hit a continue, which is kind of cool and sort of weird. I'm still trying to wrap my head around it. But yeah, they definitely should not have explained that in chapter 2. That would have lost me. I'm moving onward. Here we go. The never type is useful with the panic macro as well. Remember the unwrap function that we called on option? Remember the unwrap function that we call on option values to produce a value or panic? Here is its definition. So implement option, we have unwrap, okay, we have a match on self, some value, and then none panic. Okay. In this code, the same thing happens as in the match in listing 19-26. Rust sees the val has the type T and panic has the type apostrophe. So the result of the overall match expression is T. This code works because panic doesn't produce a value, it ends the program. In the none case, we won't be returning a value from unwrap, so this code is valid. So because we're never returning here, it doesn't invalidate the type that has to be returned, which is val, which is a generic T. Okay. One final expression that has the apostrophe is a loop. Because loop goes forever. I see. Print forever. And here's a loop. Print and ever and ever and ever and ever. Here the loop never ends. So apostrophe is the value of the expression. However, this wouldn't be true if we include a break because the loop would terminate when it got to the break. Okay. I guess that's just to cover their bases, would tell us everything, but I don't think they needed to tell us this. So if a loop doesn't return, then it's apostrophe. If it has a break within it, that means it stops at some point, which means it returns something at some point. Yes. Dynamically sized types and the sized trait. Due to Rust's need to know certain details, such as how much space to allocate for a value of a particular type, there is a corner of its type system that can be confusing. The concept of dynamically sized types, sometimes referred to as DSTs or unsized types. These types let us write code using values whose size we can know only at runtime. Let's dig into the details of a dynamically sized type called str, or string, which we've been using throughout the book. That's right, not apostrophe string, but str, all lowercase. On its own is a dynamically sized type. We can't know how long the string is until runtime, meaning we can't create a variable of type string, nor can we take an argument of type string, consider the following code which does not work. Let's see, string 1, string 2. Okay, yes. So basically what they're stating here is the pointer to string, which is size, is fine. String itself, by itself, is not size, and we wouldn't know the size until runtime. Thus, it can't be checked at compile time. Thus, this should not work. And let's just verify to see what kind of error it gives us. This does look iffy. It does look like it should work. But at the same time, yeah, mismatched types. So this says it's a different type than this. Okay, and for completion, let's just see the error down here. Does not have a size known at compile time. Yeah, because it can't be checked at compile time, it throws an error. Noted. Rust needs to know how much memory to allocate for any value of a particular type, and all values of a type must use the same amount of memory. If Rust allowed us to write this code, these two string values would need to take up the same amount of space, but they have different lengths. S1 needs 12 bytes of stores and S2 needs 15. This is why it is not possible to create a variable holding a dynamic size type. So what do we do? In this case, you already know the answer. We make the types S1 and S2 a ampersand string rather than a string. Recall that in the string slices section of chapter 4, we said the slice data structure stores the starting position and the length of the slice. Alright, so what they're saying here is that the solution is just to put an ampersand because that's a pointer, and then the pointer, which just takes the reference to where the data is actually located, and then a value to denote its current length, like the length and size, and that the pointer itself is size, so we can use pointers wherever we want to. That I do recall. So although a ampersand t is a single value that stores the memory address of where the t is located, a ampersand string is two values, the address of the string and its length. As such, we can know the size of a ampersand string at compile time. It's twice the length of a use size. That is, we always know the size of a ampersand string no matter how long the string it refers to is. In general, this is the way in which dynamically sized types are used in Rust. They have an extra bit of metadata that stores the size of the dynamic information. The golden rule of dynamically sized types is that we must always put values of dynamically sized types behind a pointer of some kind. So yeah, the big takeaway here is that if you have something that's dynamically sized and you think it should be dynamically sized, it's always going to be behind a pointer. You can only really access it behind a pointer because Rust needs to know what the size is at compile time, and you can't really do that with these things. Moving onward, we can combine string, ampersand, with all kinds of pointers. For example, we can do box string or RC string. In fact, you've seen this before, but with a different dynamically sized type, traits. Every trait is a dynamically sized type we can refer to by using the name of the trait. In chapter 17, in the using trait objects that allow for values of different types section, we mentioned that to use traits as trait objects, we must put them behind a pointer. As such, we have dynamic ampersand dyn trait or box dyn trait. RC dyn trait would work too. To work with dynamically sized traits, Rust has a particular trait called the sized trait to determine whether or not a type's size is known at compile time. This trait is automatically implemented for everything whose size is known at compile time. In addition, Rust implicitly adds a bound on size to every generic function. That is, a generic function definition like this. Function generic type t, is actually treated as though we have written this. So they put in the bound size for us automatically, implicitly. We don't really see it. By default, generic functions will only work on types that have a known size at compile time. However, you can use the following special syntax to relax this restriction. And it looks like they put a question mark in front of sized. A trait bound on question mark sized is the opposite of a trait bound on size. We would read this as T may or may not be sized. This syntax is only available for sized, not any other traits. Okay, so this question mark thing in front of the trait bound is solely used with size, is not used anywhere else. And as such, we can probably forget it immediately because it sounds like we're never going to be using this. Also note that we switched the type of T parameter from T to %T because the type might not be sized. We need to use it behind some kind of pointer. In this case, we've chosen a reference. Next, we'll talk about functions and closures. Right before we end, let's go back to this. So what they said, another change is they put this T behind a pointer because since it's possible for this not to be sized, then this must be behind a pointer because that will cover the gambit of cases. Because you can have a pointer to something that's sized, you can have a pointer to something that's not sized. And with that, we've reached the end of the video. I hope you enjoyed it. Hope you liked it. If you did, hit like, subscribe, yada, yada, yada. Outside of that, see you next time. Peace.